So in this video we will see shear stresses in beams. So here if you see, we have a cantilever beam and we have to find the shear stresses varying across the cross section. So we have seen in shear stress diagram means SFD BMD how shear stress varies across the length, but we have not seen how the shear stresses will vary across the cross section. So the simple formula is tau equal to P divided by INA. This P here is the maximum force at any particular cross section that we have to find from shear force diagram. So wherever we are finding the shear stress across the cross section, at that position we have to take the value of P maximum from the shear force diagram. INA is a inertia at the neutral axis. So this rectangular cross section I have drawn it here, and there is a center line neutral axis. So inertia with respect to neutral axis we have to take, and we have to multiply with this term. So here a y bar is the area at which first we what we have to do, first we have to take any line where at a distance y, so where we have to find the shear stress. So shear stress will vary across this cross section from neutral axis to maximum. It will vary, and it will be a mirror image on the other side. So here with respect to y distance, shear stress will vary. Now suppose we have to find shear stress at this particular fiber. So we have to take the area from that point to the final edge from that line. So this particular shaded area will be the area value. Y bar is a central distance of this particular area. So if we have to find y bar, then we have to use this for I'll discuss this. And the b is the width where the fiber we have to find shear stress. So this will be the b. Here b is uniform throughout the cross section because the area is triangular, but for circular it will vary, or triangular it will vary. So here b is constant. Now area if you have to find, then it is this b distance into the height of this area. So height we have to find by, you see, d divided by 2 will be this half section, half length, d divided by 2 minus y. If we do, then we will get this particular height. So that is how we have to find the area. And y bar, if we want to find the center point, then we take first y, and we have to add this distance times half, means half of this distance. So half of this distance, we know this d by 2 minus y. d by 2 d by 2 is d by 2 minus y is this distance, and half of that we have to take. So half into d by 2 minus y. So this is how we have to calculate y bar. We know the inertia for this particular shape will be bd cube by 12. B is this width, and d is this height. So all this value if we place in this formula, then we get shear stress at this particular fiber, and it will vary with respect to y. Now we'll see this shear stress variation with respect to some standard shapes. So first we have this rectangular, and you see shear stress will vary from 0 at the edge to the maximum at the center for rectangular cross section. This is the beam, and this is how we are looking at. And if we project this cross section, then this is how it will look from this front, and this is the side view of the beam. So here the beam will be welded if it is a cantilever. Now if you see, the maximum value of the shear stress will be 3 by 2 tau average. And tau average, you know, tau average will be simply this P maximum divided by the area. So the typical value we calculate the in standard form tau average, where P divided by area, that is how we have to calculate. Area is a B into D. So B into D. So load divided by area is the shear stress, which will be the average value. And if you want to find the maximum at the center, then it will be 3 by 2 times the tau average. Now this formula is is in simple terms. We do not have to use this complicated formula here. So we can directly find tau average and multiply it by 3 by 2 for rectangular. For circular, the variation will be same, but this tau maximum value we have to multiply 4 by 3 times tau average. 4 by 3 times tau average. Here for triangular, it is 3 by 2. It is 3 by 2 tau average. So this is 3 by 2 tau average, means half of the tau average. So all these terms we are having in terms of tau average, because tau average is easy to calculate. It is simply load at that particular cross section divided by the area of the cross section, and then factor 3 by 2 for rectangular. For circular the variation is same, so 4 by 3 tau average. And for triangular, here maximum is at the central line only, but in triangle the maximum will not be at exact center line. And tau average will be at 4 by 3 tau. Tau average will be 4 by 3 tau average, and tau maximum will be 3 by 2 tau average. So if you see, these both formula are here only. So the maximum value is 3 by 2 tau average for this triangular, and average value is 4 by 3 tau average at neutral axis. So both these formula combined will make for triangle. And this will be at h by 2, and this will be at h by 3. Neutral axis will be at h by 3. So if you remember both this formula for rectangle and circle, then it will be easy to remember for triangle, because tau maximum, tau average are both this formula. And 3 by 2 is more than 4 by 3, so definitely 3 by 2 is maximum. 3 by 2 tau average. And tau average is p divided by this is triangular area. Now for some other shapes, if we see, for circular shape where there is a hollow circular, this is circular hollow cylindrical shape, this is the cross section of that. So you see, tau is proportional to 1 divided by width, this b value. So here if you see, the width starts to increase, and after a certain point it suddenly drops, so shear stress will increase from here, and at the center point shear stress is maximum, so it will increase in much faster rate. From here to here there is particular rate, but after that it will increase faster rate, because the width is also decreasing, so shear stress is increasing, and we are moving towards the central line. So both this effect will suddenly increase. So here there will be some um, edge formation, means there is a point. Until that point there will be continuous smooth slope. After that there will be a break. So tau maximum will be at a center point only. So this is shape we have to remember, no need to remember the formula for this. For I section, if you see, this of particular flange, there is a much bigger width, so there is a small shear stress, but there is a sudden change from here to the web area, so shear stress directly have a jump in the value, and it will be much higher, and then there will be maximum value at the center, and it will increase till the center like this manner. But here this jump is because from this particular width at the flange end we are moving towards the smaller width of the web. Similarly in T cross section, here on one side we are getting this lesser, because we have a much higher width, sudden jump is there, so sudden increasing in the shear stress, and it will be zero continuously till this point. So in between there will be some maximum value. Now this particular formula a y bar, in the formula here tau, we have to calculate a y bar. So for this particular cross section, combined cross sections, we can calculate a y bar equal to a1 y1 plus a2 y2, like that it can go up to many cross sections. So here 1 and 2 are the cross sections, so area of this, and area 1 and y1 will be distance from this neutral axis to y1 point, plus area 2 is this area of the web, and y2 will be from this particular center point to the neutral axis of this combined shape. So that is how we have to calculate a y bar. Directly we can calculate and put it in this formula. And b value here and here will be different. So there are two b values. So this is how the shear stress varies. This final shape, if we see here, this is the rectangular, and if you see here, this is actually a square shape. If we rotate it to 45 degree, then we will have this shape. Now from neutral axis the distance is h by 2, and tau maximum occurs at h by 8 distance from this neutral axis. So here if you see, width is increasing continuously at the center point, and if you are moving toward the center point, shear stress will increase, and shear stress is inversely proportional. So both this combined effect will slightly decrease here shear stress, because with increasing with influence shear stress much more than the distance from the center line. So here, if we, from zero value there will be tau maximum and then there will be tau average. So tau at neutral axis, this is not the exact tau average of this entire, but we call it tau average because it is at neutral axis. So here p divided by area, the area of this, and p is the load at any particular cross section from this side view of the beam, like this. If we move from the see from the side view at any particular cross section, if we plot it, then at that particular point we have to calculate this shear force from the shear force diagram. And tau maximum will be 9 by 8 times tau average, which will be at a distance of h by 8 from the center line. So this shear stress is sometimes asked in examination, and it is much unique concept which is different from SFD BMD. And this shear stress is often neglected because it is much lesser than bending moment, and the beams are designed for bending moment. But this shear stress we have to qualify for various beams, so to make sure, to make sure that the beams does not fail in shear failure. And this shear stress will fail the beam in this lateral direction because the tau maximum is occur at the central line. And one important point, if we plot this, if we give apply the load at this shear center, so for this all particular points there is a shear center point. Maybe we'll discuss it in the future video. But if we provide a load, this particular load value at the shear point, any w or any some random load, if you apply at the shear point from this cross section, so this cross section will have some shear center. Let's say for circularity is center point. So here if we apply, there will be no torsion in the beam, otherwise there will be torsion in the beam. Similarly for other shape there are different shear center. For like L section it will be outside the cross section, for I section it will be somewhere in the center. So like that we have to apply the load, so there will be no torsion in the beam. So thank you for watching this video, and we'll see you in the next video.